All right, folks, we are back studying section 12.23 on what's he's going to call Bayesian PCA. So the context for this is that we've been doing probabilistic PCA, where we're trying to explain our data as coming from some linear projection of some latents plus an offset corrupted by some isotropic noise. And what we care about here is determining the size of that linear space in which the data is supposed to kind of be living in. And the question is, how to do that. And what he's going to do is he's going to describe a few ways of doing it, the proper Bayesian way of doing it among those. And then he's actually going to describe a really interesting, maybe an approximation to that, which is going to be based on this concept of automatic relevance determination. So it's going to kind of automatically determine how big the subspace should be, how many dimensions it should have to capture our data. So that's kind of going to be the focus of this section. Now, I think he covers the main points pretty well, but he doesn't kind of go into too many of the calculations. So I've done that in a note on my blog. So what I'm going to do is we're going to go through this section, highlighting the key points. And then after we're done going through the section, then we'll switch over and we'll go through the notes that I've made, which flesh out some of the points, just in some more detail, so you can see kind of how it's done. And the main concept here is just going to be, how do we use kind of automatic relevance determination to determine how big the subspace should be. So that's, I think, a cool idea, something worth taking home from this section. So let's get into it. Okay, so we assume that so far in our discussion of PCA, we have assumed that the value of m for the dimensionality of the principal subspace is given. Okay, so in practice, we must choose a suitable value according to the application. For visualization, we generally choose m is equal to 2, so you can actually plot the data, look at it, m equal to 2 or 3. But for other applications, you might not know. Now, one thing that's kind of quite common is what you'll do is you'll, for example, make these plots of variance explained, or the remaining variance unexplained, and you look for like these little elbows. So like if you like plot, this will be like the, can you guys see this? Yes. So it's like principal component 1, 2, 2, and then maybe like 3, and then this kind of, they're all going down like that. And you're like, oh well, okay, it looks like there's kind of an elbow between 2 and 3, so I'm gonna pick like this is like unexplained variance. Unexplained variance. You do the same thing, with the explained variance. Of course, it's just 1 minus it, and it kind of maybe it looks like this. And you look for kind of an elbow like that, and it's very imprecise. Often, honestly, it doesn't make too much of a difference. But okay, it's nice to know. Is there like a non-heuristic, non-qualitative way to determine how big a subspace we should use? Okay, so he's talking about this. So when we look to see if the eigenvalues naturally form two groups comprising a set of small values separated by a significant gap, what does significant mean? Unclear, from a set of relatively large values, indicating a natural choice for m, but in practice, such a gap is often not seen, and that's indeed been my experience as well. So how do we do this kind of in a more rigorous quantitative way? Okay, so now we're going to kind of look at, we've got this probabilistic model, so maybe we can kind of leverage that somehow. So because the probabilistic PCA model has a well-defined likelihood function, so that's going to be like, the probability of our data given those various parameters. The W was the columns of W span the subspace that we thought data came from. We've got mu, which is going to be the offset of the data, and then the sigma squared, the additive variance, the noise variance basically on top of that. So he's saying, well, we have some options now, right? So we could employ cross-validation to determine the value of dimensionality by selecting the largest log likelihood on a validation set. So essentially what you would do here is you would fit your data, you would have like a bunch of different models. Each of them, the W would have like more, 1 dimension in one model, 2 dimensions, so on and so. You would fit the data, of course, on your training data. The larger the number of dimensions, the better it would fit. But then what you do is then you compute, now you instead of comparing the probabilities on the training data, you would then compute this probability on some left out data using the W's that you learned for each one of those models, and maybe then you could just pick the model that has the largest log likelihood, on the largest likelihood on the held out data. So that would be kind of one approach. But he says, look, such an approach can become computationally costly, and then if you got like a more complicated models, it can become a little bit maybe it becomes harder to compute. Okay. Now it says, given that we have a probabilistic formulation of PCA, it seems natural to seek a Bayesian approach to model selection. Okay, so this is kind of where the Bayesian PCA, I think, comes from, right? Because there are lots of ways of it. If someone told you, I'm going to talk about Bayesian PCA, what does that mean? Like maybe that means I want to get posteriors on W mu and sigma squared, given some priors and the data. But I think what he's talking about in this section is using a Bayesian approach to model selection. So picking the dimensionality of this, of W, basically, how many columns it has. So to do this, we need to marginalize out the model parameters with respect to the appropriate prior distribution, right? So essentially, again, you would what you would do is you would have a variety of models, right? So you would say, let's say the D equals 1 model. I think actually this should be called M, right? So W is equal to, just W1 correspondingly. And now you would say, okay, well, what is the probability of our data given, M equals 1? So that would be, the marginal likelihood. And so then this would be, well, you would kind of integrate out this W, blah, 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 times the probability of given your model, dW. And that would give you, that's in principle how you would do it. And then you would compare those. Okay, so these are the marginal, again, the Bayesian approach, you're going to be working with marginal likelihoods, right? You've marginalized out all of the parameters that you don't care about, and all you have left is just the probability of one model, basically. The probability of a model, when you integrate it out, all of the parameters weighted by how well they fit the data and their priors, right? And that's kind of the Bayesian idea, that if this will kind of naturally, the more complicated models will be kind of penalized because they can explain a larger variety of data sets, not just yours. The marginal likelihood values given by the variational lower bound. So let's back up. So this can be done by using a variational framework to approximate the analytically intractable marginalizations, which is this guy. The marginal likelihood values given by the variational lower bound, which we talked about a little bit in the EM section, can then be compared for a range of different values, and the value given the largest marginal likelihood selected. Okay, so again, comparing approximations to these and picking. Okay, so now what we're actually going to talk about today is, and we talked about this idea of evidence approximation before, but we're going to consider a simpler approach introduced by, based on the evidence approximation, which is appropriate when the number of data points is relatively large and the corresponding posterior distribution is tightly peaked. So it involves a specific choice of prior over W that allows surplus dimensions in the principal subspace to be pruned out of the model. So this is a cool thing, right? So somehow we're going to pick some, we're going to have W be determined, have some priors on its elements, and then we're going to hope, and he shows in another section of the book, that basically what will happen when you fit the data, and presumably in the appropriate setting, that some of those when you fit the parameters, those hyperparameters, those corresponding to columns that you don't need will effectively force the corresponding columns to go to 0. So that's kind of the basic idea. When we'll obviously we're going to talk about, that's what we're going to be talking about in this section, basically. Okay, so let me erase all this. Okay, cool. Okay, so this corresponds to an example of automatic relevance determination, which will have been discussed in 7.22. We haven't covered it yet, so we're just going to power through. We define an independent Gaussian prior over each column of W. So let's highlight this. This is kind of the key idea, right? Which represents the vectors defining the principal subspace, right? We knew that from before. Each such Gaussian has an independent variance governed by a precision parameter alpha I. So this is let's highlight this, because this is kind of the important, the key idea here. And notice what's happening, right? So essentially all what we're doing is we're looking at, so let's look at, you guys can see, so W is going to equal to, W1, these are columns, W2, Wi, etc. Okay? And now what we're saying is we're going to put a prior on the elements of W in such a way that all the elements in the same column have the same precision. So it's going to be a Gaussian prior with mean 0 and precision alpha I, And notice that the alpha only depends on what column you're in. So all the elements of this column, they have the same precision. So we can actually, one way to write this different, and to see where the d comes from is you can just write this as x minus 1 over 2 alpha I wi1 squared times x minus 1 over 2 alpha I wi2. Sorry, I need to write this more cleanly. wi2 squared, etc. So all the way to x minus 1/2 alpha I. You see the alpha I is not changing. In principle, you could have a different variance for each of the elements. But what we're going to do, this is going to be alpha I d squared, right? And each one of those is going to contribute one of these terms. And then we have d of them, so you get the d squared. So essentially, we're putting a prior on the elements of w, but in such a way that all the elements in the same column have the same precision. Okay, so the same precision term. So now, one way to think of the precision is you can think of it as a penalty on how big the wi's get. And so you can imagine that if you fit the alpha i's and somehow magically these alpha i's get driven to infinity, then the corresponding columns are going to be forced to 0. That's the idea. So they will kind of be automatically removed from the model. Their weights will be set to 0. They won't contribute. Their latents won't contribute. That's the idea. Now the reason why that will happen, I mean, like, why is it that we would expect that to happen? Maybe the alpha i's could go to some intermediate values, etc. He discusses it in an earlier section, which we'll cover when we get there, when we loop back. Yeah, so just for now, we're just going to assume that this very nice thing actually happens, and we can kind of see why, okay, in some setting, if we're lucky, why that would have the effect that we want it to have, why it would actually end up removing the elements from the model. Okay, so now how do we actually, and we're going to get into, we'll discuss kind of some of more of the details in the notes, but let's just go through what he says. So the values for alpha I will be found iteratively by maximizing the marginal likelihood function, which w has been integrated out. Okay, now the key thing is, as a result of this optimization, some of the AI may be driven to infinity. So let's highlight that. That's important. Some of the AI may be driven to infinity with the corresponding parameter vector being driven to 0. So that's kind of the key idea. Let's put some arrows on it. The effective dimensionality of the principal subspace is then determined by the number of finite AI values, and the corresponding vector wi can be thought of as relevant for modeling the data distribution. So that's kind of the automatic relevance determination. In this way, the Bayesian approach, I'm not so sure this is like really the Bayesian way, but anyway, let's just take his word for it, is automatically making the trade-off between improving the fit to the data by using a larger number of vectors of wi, with the corresponding eigenvalues lambda I, each tuned to the data, reducing the complexity of the model by suppressing some of the wi vectors. So I think some of those details are going to be explained earlier, but the key thing is that there is this possibility of kind of trading off the complexity of your model with the goodness of fit. Okay, so the values of AI are re-estimated during training by maximizing the log marginal likelihood. So the likelihood is here, and now we're going to have to do this, we're marginalizing out the parameter values correspondingly. Now this is going to be, and so note that for simplicity, we also treat mu and sigma squared as parameters, and we don't have priors on them. So we're just going to focus on, you could make this more complicated. There is a link to a paper that does this, but for now, let's just focus on W. This integration is intractable, so these formulas are going to be complicated. We make use of the Laplace approximation. Now, Laplace approximation is basically you approximate an integral by its peak value and some kind of volume term. Now, if we assume that the posterior distribution is sharply peaked, then the re-estimation equation obtained by maximizing the marginal likelihood with respect to alpha I take the simple form. So it's kind of this iterative, you get your w's, you get a new set of alphas, use that alpha to determine w's, etc. In the notes, I'm going to show you that there is actually, we don't have to appeal to the Laplace approximation. We can just do all of this using our EM framework, because that's essentially what we're going to be wanting to kind of leverage here, right? We've already got these EM machinery they worked out last time for doing this iterative updates to W and mu and sigma squared. Now ideally we just want to update that slightly to account for these precisions on the columns. It turns out we can do this. It will look like this. I will show you where this comes from. And it turns out that you can actually also compute this as part of that. You can just compute that because these alphas are just parameters again, right? So you can do an m-step update. Remember, in the m-step, we maximize a particular, expectation with respect to the parameters. Well, if you do that, you can actually you would get the same expression. So I don't think you need to necessarily appeal to Laplace approximation. Let me know if you think we do. You can just do it all within the EM framework, basically. Okay, so we'll get to all of this in the notes, but let's just continue for the moment. So if we choose m equals d minus 1, so remember, this is the largest dimensionality we can take. It's minus 1 because one of the dimensions has been removed due to our data having the mean being put in a separate variable. If all alpha I values are finite, the model represents a full covariance Gaussian, right? So that means that like you're the best, if you figured out that actually you need all the dimension, you can't really dimension reduce. Well, if all the alpha I go to infinity, the model is equivalent to an isotropic Gaussian, right? So that means you don't actually, the projections or the subspace information is useless. All you're left with is just the noise term and the mean offset. So it says your data basically just looks like a Gaussian ball. Right. And so my model can encompass all permissible values for the effective dimensionality of the principal subspace. It is also possible to consider smaller values of m, which will save on computational cost, but which will limit the maximum dimensionality of the subspace. Yeah, so for example, he's just saying, look, if you have an enormous, like this whole thing will give you the right answer, hopefully, will have the possibility of giving you the right answer if you set W to allow for as many dimensions as you could possibly need, which is this, and then have it figure out which ones it should actually use. If you now, sometimes that's not very practical, so you want to use a smaller value of m. Okay, so that means that it will limit the maximal dimensionality of the subspace. So that's kind of an obvious point. And the comparison of the results of this algorithm with standard probabilistic PCA is shown in 12.14. So let's have a look. It's actually a pretty cool figure. So the idea is this is W. This is kind of, let's say this is W in W, and then this is W. Let's call this with ARD. Okay, so you kind of learned. So in both cases, I think he's got like the synthetic data set comprises 300 data points in d equals 10 dimensions, sampled from a Gaussian distribution having standard deviation 1 in 3 directions and standard deviation 0.5 in the remaining 7 directions. So it's kind of there are some 3-dimensional directions of higher variance relative to the background. Okay, the left-hand plot shows the result from maximum likelihood probabilistic PCA. So you see how all these weights, all of them are it's learning some weights. So you've told it I want 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like 9 dimensions. Now, because that's d minus 1, 9. But if we use this ARD, well, you see basically just the largest dimensions are kept. So that's pretty cool, right? Like W is still 9-dimensional, but effectively there are 9 columns, but actually only 3 of them are non-zero. So the actual dimensionality is 3. So that's like pretty awesome. It's kind of figured that out. So you see how the Bayesian model is able to discover the appropriate dimensionality by suppressing the 6 surplus degrees of freedom. Okay, so that is pretty awesome. Now, Bayesian PCA provides an opportunity to illustrate the Gibbs sampling algorithm. So we haven't discussed Gibbs sampling, but the idea there is, when you want to generate samples from a probability distribution, sometimes it turns out that if you knew the value, if you condition on all the, you'll usually have kind of a vector of parameters. If you condition on all but one of them, then sampling from sampling the distribution of the remaining one is easy. Turns out if you kind of do this iteratively, then you will end up with getting samples from the joint distribution after some long time, which we don't know how long it actually is. Okay, so essentially what he's doing, so we'll just touch on this. We're not going to go into any depth because we haven't covered Gibbs sampling, but let's just see what he says. So an example of the samples from the hyperparameters ln alpha I for a data set in d equals 4 dimensions in which the dimensionality of latent space is 3, but in which the data set is generated from a probabilistic PCA model having one direction of high variance, with the remaining directions comprising low variance noise. So we're going to have this model. We're going to then want to sample from the alpha i's that actually fit this model, basically. And essentially what he's saying is, if you look at this, it looks like at any given time, yeah, so notice that we've got so at any given time, only one of these values of alpha I is 0. So when alpha I is when alpha I is small, it basically means that that column doesn't have a penalty. And you notice that at any given time, there's just one of these columns, one of these alpha i's that's small, right? So there's 0, this is 5, 5, and so on. So essentially, just one of these directions is being picked out, which is kind of indicating that your data set is actually one-dimensional, which it is by design here. So it's also clearly the presence of 3 distinct modes in the posterior distribution. At each step of the iteration, one of the hyperparameters has a small value, and the remaining 2 have large values, so that 2 of the 3 latent variables are suppressed. So that's kind of what we want it to be doing. During the course of the Gibbs sampling, the solution makes sharp transitions between these 3 modes. Yeah, and I wonder in that setting, like, as the alphas are changing, presume maybe like the weights are also changing over time, so that essentially, like, they're kind of just swapping which variable is actually capturing the direction of the data, and the other 2, the weights are. But yeah, that'd be a fun one to kind of look into, but we'll leave that where it is because we haven't covered Gibbs sampling yet. Okay, and then finally he just says, look, the model described here involves a prior only over the matrix W, and you can kind of do priors, over the whole thing, and you can, if you want all the details, they're here. And also variational approaches, and you can touch on them there. Okay, so that's kind of what the ARD is in applied to the PCA in a nutshell. So now let's go and just look a little bit. So I wrote some notes based on this section, essentially telling us where all these formulas come from. So you kind of maybe get a bit more of the details. This is essentially stuff that I derived, so I think it's correct, but you guys let me know if you disagree. Okay, so let's go back here. Here we go. The principle of subspace describing data is spanned by the columns, so we already talked about this. Now the proper Bayesian way, we talked about that. You compare marginal likelihoods with different values of m, and you pick the one that has the largest one. But we're going to be using this automatic relevance determination. And we talked about, okay, so we put this, this Gaussian prior, and we talked about where that comes from. So we're putting this kind of precision or kind of a penalty on all the weights, but using the same penalty for the weights that come from the same column. So we are going to kind of, rule out columns one at a time, entirely rather than elements. Okay, and so when we optimize the values of alpha, we hope to find that some of the precision will be driven to very large values, effectively forcing the corresponding column values to 0, reducing the dimensionality spanned by W. So, and Bishop talks about this in 7.22, so when we get to that section, presumably we'll understand why that tends to happen, but at least the possibility is there. Okay, so now let's look at, so now this becomes our model for PCA, for probabilistic PCA with ARD. If you haven't seen this before, it's just kind of a simple notation. So essentially we've got the plates here, which says there's n copies of x of n. So these are observations, but each of them is determined by its own latence. So this is kind of the probabilistic PCA thing. There's also a variance that can describe that, the mean offset, the weights. But now the weights, unlike in probabilistic PCA where the weights were a parameter, now they're almost like a latent variable. So we're going to need to, let's say, integrate over them or deal with them somehow, do EM on them. And there's our new parameter alpha that's going to determine, that's going to be the penalties on the weights. Okay, so now our task is going to be, as usual, is going to be maximize the likelihood of the data, right? So notice we've got our data here, we've got the mean, the sigma squared, and now it's not W anymore, it's alpha, right? These are our parameters. But now we've got latent variables. So we've got the Z of n, the latence for each data point, but we've also got W now. So W is a latent variable as well. And so we're in this kind of latent variable, maximum likelihood and then latent variable model. We're going to apply EM, right? We've got all this machinery we developed last time. We want to be able to use it again. Okay, so remember what we did. So we start with the full data log probability, right? So here is X, this is our observed data, latence that we don't know, and latence for each observation, and then the weight vector that we don't know. These are our parameters. Okay, so now we want to relate this to our probabilistic PCA again. So we're actually just going to write this out, using the basic rule of probability as this sum, right? So we're just going to put, what is it, the product rule of probability or whatever it is. So we're going to write this as, remember, so we've got P of x z w is P of x z given w times P of w Okay, that's all we're doing here. Now notice that this first part is just what we had in probabilistic PCA, And the second part is a new thing that we're getting from automatic relevance determination. W doesn't depend on mu and sigma squared, just depends on alpha. Okay, so now it says notice that z doesn't depend on alpha. So now we're going to do the EM thing, right? So in the E step we set z to be its true posterior distribution given everything else. But z only depends on doesn't depend on alpha, right? So all dependence that z has had is exactly what it had in the same as before. So the same that we had in probabilistic PCA. So our E step updates are the same. Now the M step updates are also the same because again they only depend on this part and it hasn't changed. So this is the same as in the vanilla probabilistic PCA case. So the only thing that changes is the M step update for W, because now we've got this alpha term basically, right? We've got this, which is just like what we had before. Now we've got this additional term that depends on alpha. So to determine that, we compute the expectation relative to the latence of the log full data joint. So again, so this is just the standard EM machinery. And if you look up the formulas from you'll see that okay, we've got this term just like before. We've got this term just like before, and now we've got this additional term, okay, which is coming from the prior. So now the only thing we have to do is to make things work is we're going to rewrite this last term. Okay, so we're going to write this again. These trace properties are super helpful. So this is a scalar value, so it's equal to its trace. But now we're going to use the circular property of the trace and move this W to the other side. And now if you notice this actually is the same as the trace. So this bit in here is the same as W times the diagonal matrix times W transpose, right? So this is just, if you look at this, W1 to WM, and you got, alpha 1, alpha M, and so on. I know you can't see the rest of it. If you just multiply this out, you'll see that it's actually the same as this. And then to kind of make it symmetric and useful with what we have above, we're just going to use, again, the rotation property of the trace and just move the W on this side. So now this guy over here lines up with that guy over there. And so all we do is we just modify, we just modify the update, right? So when we had this before, notice it has a sigma squared, there's a sigma squared here. We just kind of drop that sigma squared term. So that means we have to multiply this thing by a sigma squared because it doesn't have a sigma squared hanging out on it. But everything else is the same because essentially these, we're just kind of lining up these guys. I think, yeah, and I was just worried about a factor of 2, and there should be a factor of 2 here, and that's why. Yeah, perfect, good. So right, so the only thing that's missing is this guy now doesn't have its sigma squared is gone, so we multiply by sigma squared. So we do the same thing over to the diagonal of alpha by the sigma squared. That's what we have. And so this is basically the equation 12.63. Okay, you just derive it by doing the M step as usual, but just augmented now to account for this additional prior term. Okay, so now he actually continues in the book. He just kind of goes on that this is the update. It's actually kind of interesting to see like what actually happens with this update when some of these alpha values are infinite. So we're just going to consider the case when one of them becomes infinite, and because then we'll get the general case. So let's assume with the loss of general that the one that's infinite, got driven to infinity, is the first one. You can always shuffle things around, relabel things so that's the case. So we're going to consider, okay, so the way we're going to think about it is we're going to look at, we've got the sigma squared times, this thing. It's just going to so happen that the very first one, we're going to have a lambda term. This was thanks to ChatGPT for this approach. Now we're going to drive lambda to infinity, right? That's going to be that alpha value. Okay, so now you can just use formulas for inverting block matrices that effectively what happens as lambda goes to infinity is that the inverse of this matrix, so notice what it is, right? We've got the corner, we've got some terms up here corresponding to that, that first row and column, and then we've got everything else. Well, it turns out that as lambda goes to infinity, the inverse of this matrix ends up being 0, 0, and C minus 1. So effectively, you're just removing the influence of that kind of first element and just having the inverse of your data, of the kind of submatrix, the subset of your data that didn't involve the very first term, which kind of makes sense. So then when you then plug things in, so now this is the inverse that you're plugging in, what you'll see is that, because these are 0, the very first column, you know, you're going to multiply this by 0, 0, you're going to get a 0, right? So that first column is going to be set to 0. And now the influence of now, and then to determine the remaining columns, where you've got this sum that's multiplying 0 and c, but you'll see that when you actually multiply, this expectation, well, what's going to matter is actually going to be the second element, because the very first element every single time is going to be set to 0. It's going to be multiplying 0. So effectively what that's going to do is going to remove the first column of W and also remove the influence of the first latent variable. And so effectively that whole dimension just drops out from the model. So alpha I removes the corresponding column Wi from the model as expected. Okay, so that's kind of giving you a sense of what actually happens, you know, how our update gets changed when the alpha is driven to infinity, and how that determines the weights that we learn. So it sets those weights to 0 as we hoped. Corresponding latent, because it has a prior on it, it's going to get driven to 0. Okay, now this all assumes that we're given alpha. To determine it, how do we determine alpha? So Bishop says we should look at the likelihood of the data, which is, you know, the marginal likelihood, right? So we're going to integrate out the effect of W. The integral is very intractable, so we're going to assume it's sharply peaked, maximize it, take the value of alpha at that maximum. That's only going to depend on this because alpha doesn't show up there. So effectively, you're just going to be given your previous value of W, determine a value of alpha that's determined by maximizing this. Okay, and that gives the formula in the book, but I don't think we need to do this because we can just do EM, right? We're doing EM, so why not just do an M-step update for alpha as well? It's just like it's also a parameter. And so if we look at that expectation of the log joint, well, alpha only shows up in this term, right? So when we maximize it, like we're maximizing this, it actually is the same as maximizing this. So we're going to get the same answer basically. So let's just do that. We maximize it. Here it is. We just take the logarithms as usual, we differentiate, set to 0, and we get the same formula that he does. So I think we can actually just treat the whole thing within EM. We get the same answer. The alphas are updated just with an M step without having to appeal to the Laplace approximation or any of that. Okay, and I think that's basically all of it. So just wanted to show you a little bit about where those formulas come from, how we kind of extend, just apply EM with a slight extension to accommodate this prior on the weights, and to kind of show you what happens if those alphas actually go to infinity, which means they get eliminated. So it's kind of a cool way of automatically determining the relevance of the columns of W to explaining the data. Okay, so hopefully that was useful. You learned some stuff. Please let me know what you thought. If you agreed with everything, you didn't agree with some of it, always happy to hear that. And hopefully I will see you in the next video where we will talk about factor analysis. So take care.